Hi everyone and welcome back. Brahim Siddiqui with you. This is a continuation of a series of, um, if I can say, courses or knowledge sharing about the new concept in project control. My apology from last week or last video regarding the when I was talking about the when I was talking about the the buffer here. So I said that you take the duration and then you time it by the overshoot, which is wrong. So it should not be I should not time it with the overshoot. However, it should be, it's a multiplication between the duration. So between duration time, the maximum distortion, and then which will give you 13 time maximum distortion. We found that it is this value 2848.4. It's 0 2848.4, I guess 48.4. Okay, so if we do the calculation, so we found 13 times 0.28484, 3.7, approximately 4 weeks. So this will be the maximum duration on top. So I mean the maximum duration will be 13 plus 4, so it should be 17 weeks is the maximum duration. Okay. And today we will be talking about the contingency cost. What I showed you last time is a contingency, not the maximum duration or maximum risk premium. So also we said that H is x0 time epsilon max, and I guess we found it here. 2278 $2278.72. This is the H, so the high and low, so which is the x0 plus minus H. Same thing for the duration. So we say high duration. I mean, it will be duration plus minus HD. Okay, so I hope that it's clear, and let's learn a new stuff today. Okay, so and then I will define that contingency cost is what? So we call it XCC or X or delta XCC is X0 time the overshoot, and the contingency for the duration. It will be so delta DCC equal duration time overshoot. So if we calculate their value, so we know the budget, which is 8,000, time the overshoot was 40 to 46 divided by 100. I believe it's this is the value 46.42. Sorry, it's 46.42. So which means delta x cc equal 8,000 times 46.42 divided by 100. So which means 3713.6 dollars. So which means on top of your budget, so if your budget is 8,000 plus minus delta x cc, and delta x cc is your contingency cost that you need to add. So in terms of duration, so we found it last time. So we said it's 13 times 46.42 divided by 100. So, and we found that, so 13 times 46.42 divided by 100, it's about 6 weeks. Then you can see that something is not right. You can see that something is not right, because when you look at the maximum duration that that just now we calculated is 4 weeks, and the maximum duration for the contingency is 6 weeks. So which means our contingency here it's higher than HD, which is not right. And this is because of the value of the overshoot. So which means that's why you have this perturbation. That's why you have this oscillation in your project, in your activity. Or so and then we said that if we want to do something to make it smooth, so we need to reduce the overshoot. And now, how are we going to reduce this overshoot? What is the best value of this overshoot? So, so reducing the overshoot is based on your risk mitigation and the decision of the project management team, and also based on your historical data. So if you have, excuse me, if you have historical data, then you will be able to produce your systematic risk, historical systematic risk, and based on your historical systematic risk, you can compute your risk appetite, your historical risk appetite sensitivity factor, and then you get your the historical overshoot. So so now, if what is the historical overshoot? The so the historical overshoot in your, and then you can get this through your historical data. How? And this is what I am going to show you. Okay, so remember that I mean, if I call the way we produce I mean, the historical systematic risk and also the historical risk appetite sensitivity factor. So assume that you have activities A, B, C, D, E, F, G, H, I, G, K for a project. And this project one, project two, project three, they have their actual cost for activity A, actual cost for activity B, C, D, and so on. Okay, and then it's repetitive. It's the same pipeline. For example, you do the same. It's the same procedure, same activities. Okay, and this is how much it cost you in the past. So you have done this project for 20 times. Okay, but every time you have a different cost, maybe because of the location, because of I don't know, fluctuation of cost, because of many factors. So you collect your data, actual cost, and this is what you get. Okay, and then you take the sum for each line, total cost for each line. Okay, so this is the total cost for each project and the breakdown by activity. All of these are actual costs. And then you do the formulation of the systematic risk, which is the I showed you last time. Is the you calculate the covariance over the covariance between this column, let's say between this column, okay, and the total cost this column. So you take the covariance between them, and then you get this covariance value. And then you divide by the variance of this column. So this is the variance. So when you take this, you divide by this, you get a systematic risk. This is how it was defined. Okay. And what is the risk appetite sensitivity factor? You just plug it into this formula. So you plug it into this formula. Now you know the systematic risk. You plug it, you get the risk appetite sensitivity factor. These are historical um, risk appetite and sensitivity factor. So if I write here, I say the beta historical is we found how much we get it. It's 0.13094. 0, 13094, and each it's 0.31990. 31990. 31990. Is that correct? 31990. Okay. And this is for activity C and so on. Okay. So now what can we, how we can reconstruct, how we can get the historical overshoot. Okay, so if you, let's recall this equation. Okay, so we have, yeah, so um, we have, let's see, so we have beta time logarithmic of 1 plus E1 over beta over 2 equal half. And we said 2 plus overshoot over 1 plus overshoot. Okay, so now for historical systematic risk, what is the value of the overshoot? So which means we need to solve for overshoot, historical. So we know if we substitute um, historical systematic risk in this equation, what we will get. So let's do the math here. So which means that I will get, if I call this A, because it will be a constant value, okay? So I will have A equal half of 2 plus OS overshoot, 1 plus overshoot. Then I will solve this to find overshoot. So which means I will get 2A 1 plus overshoot equal 2 plus overshoot. So which means 2A plus 2A overshoot equal 2 plus overshoot. And what's gonna give me? So I get 2A minus 2 overshoot minus 2A overshoot, right? So which is overshoot equal 1 minus 2A. This apply that overshoot equal 2A minus 2 over 1 minus 2A. Okay, I believe it's correct. So so let's double check here if I made any error. So I have 2A plus overshoot 2 plus okay, and then 2A plus 2A overshoot equal 2 plus overshoot. So I will bring this in the other side and then bring this in the other side, so it will be OS minus 2A, and then we will have O. Then here we will disapply that. What happened here? Here is what it's overshoot 1 minus 2A. Then we have 2A minus 2 over. Yep, so correct. So this is the overshoot expression, knowing that A is a function of historical systematic risk. Let's calculate A. So let's do the, okay. So we have, okay, I start logarithmic. I have 1 plus, and then I have E to the power of E, no. So we have this. I have 1 divided by 0.13094, like this. No. So it's, I I have to do it one by one. Okay, so okay, I have 1 divided by 0.13094. Okay, take the exponential. Okay, and then plus 1. Okay, and then I divide by 2. All right, and then I take the logarithmic, and then I time it by 0.13094. So I get 0.0, yeah, 0.9093024. Okay, so then I will calculate the overshoot, the historical overshoot. It will be time 2 minus 2 divided by 1 minus 2 times 0.9093024 and 0.22, 0.2216. So approximately 22.16%. So now we can say the historical overshoot is 22.16%. Okay, so now and what is the budgeted overshoot of the system? We found that it is we found it here 46.42. 46.42. So you can see that the budget that was given to us, the system budget, we have X0 equal 8,000 and F0 it was 5,000 and variable cost or direct cost 3,000. And then from here we got we managed to compute the overshoot. We managed to calculate this as the risk damping. We managed to risk frequency. We managed also to compute the systematic risk beta, and we found that beta was 0 was you see here. This is what we did last time, beta, and we managed also to calculate the risk appetite sensitivity factor. So we managed to calculate the duration. Too many parameters. These are the design performance metric of this given budget system. Now we are evaluating this against what is in what you have done in the past, and you will decide by yourself if you are in accordance on following the same pattern as previous execution of your project or something different. And then there will be discussion within the project team to come up with the right overshoot that will make sense to your project, and you can manage your project in more accurate way. Okay, so now we have the overshoot, historical overshoot. Can we compute the historical system risk damping? Can we calculate the the historical risk frequency. Can we calculate the, the duration, historical, the maximum duration, historical, and so on. So you can see that we have a lot of things to be calculated, and also the XCE, and many things that we can, this is just to name it. Okay, so now we have the overshoot. Let's calculate the risk damping historical. So this is for historical risk damping. We know that, let's keep the same color. So we know that risk damping equal minus log overshoot divided by 100 divided by the square root pi square plus a log overshoot divided by 100 square. So, and this overshoot is historical, so which means we need to use this value. So by substituting this value, what we will get, let's do the math here. So, okay, so it's already divided by 100, and I will take the logarithmic and then square it. Oh, no. So I will take the 0.2216, and I will take the logarithmic, okay, and no, okay, so we say I have pi square plus open bracket 0.2216, and I will take the I will take no, don't like this. So we take the logarithmic, and then I will say 0.2216. I close the logarithmic, and then I close this, and then I take the power, and then I take the square root of everything, and then I take the inverse, and then I time it by the logarithmic of 0.2216, and then I have to time it by -1, and I get 0.4325. You see how it was, how the risk damping increases. This is the historical one, but the budgeted one, it was 23, I believe. 23,717. 23 was the 23.23717. So it's a big jump here. Okay, so now everything, it's gonna change. Excuse me. And we can do also for the omega n, historical, of course. And we said that this is uh, risk damping plus minus 1 plus, this is historical, sorry. This is historical, and this is historical, and this is what we will get. This squared plus 1, take the square root, and plus 0.4325. It's 1.522. You see, it's also different than the of the system, which was 1.265. So it was 1.265. Okay, so what we can do also, we can calculate the duration. So the duration of historical duration, which is approximately 4 over risk damping risk frequency. So the original formula is minus logarithmic of delta over omega n. And delta, we said it's about 2%. That's why we give you 4. Okay, so and this will equal what? Let's keep the same formula. We don't, so we have 0.02 logarithmic time 1, because there is a negative sign. And then we divide by the historical risk damping 0.4325 time the historical risk frequency 1.522. Then we get approximately 6 weeks. What is D of the system? Approximately, and we found 13 weeks. So this gives you an idea on how the distribution of your budget. So there is many ways on how to rearrange this budget system. So the historical, say, 6 weeks. The current given budget system, say, 13 weeks. So what was, how we can manage that? We will see this shortly. Okay, so what else we can compute? So we know the historical. So we know historical beta, and then this is 0, 1, 0, 1, 3, 0, 9, 4. The systematic risk for the system, and then we found that it is 0.23328, 0.23328. So the risk appetite sensitivity factor for the system is how much? 0.6831, 0.6831, and the historical, we just is 0.31990, 0.31990. So if I take this, we know that gamma is historical over the systematic. And this will give you what? 0.319990 and then 0.6831 and 0.31990 divided by 0.6831, no, 0.6831. So it's about 0.4683. So this is the gamma. Now, if I want to write the equation of motion or the historical governing equation, which is the acceleration of the distortion plus 2 risk damping zeta time omega n risk frequency time the velocity of the distortion plus the squared of the natural risk frequency time the distortion with respect to time equal gamma time risk natural risk frequency squared time ut. And then, so we know that this is what? Plus, so we know everything here. So we know the historical, we have 2 time 0.4325 time 0 time 1.522 522. So this gives you 1.3163 plus 1.522 squared 2.311648 time equal gamma 0.4683 time, don't have space here, time omega n, which is 2316 time ut. So, and based on this, we can get the transfer function, the historical transfer function, the transfer function defined, historical defined in the Laplace domain, and we have gamma 0.468. If I do the math here, time 0.4683. So this equal 1.0848, and then we have s squared plus 1.3165 s plus 2.31648, and that's it. Okay, so this is our transfer function of the historical budget system, and we said that from this now you can simulate your curve, and you can see that by using the program or the Python I showed you last time, you are going to reduce this here, and we can calculate the maximum the maximum, because now you have the historical overshoot. What is the maximum distortion historically? So the maximum the historical one, and we said that this is epsilon at the steady state time 1 plus the overshoot for historical, and now this will depend of this steady state, and we said if we keep it the same, if we say epsilon ss equals 0.2, then the maximum historical distortion, or when we say maximum, it's basically the amplitude, the magnitude, the maximum, the amplitude of your distortion. So it is 0.2, 1 plus, what is the new overshoot? 22.16, correct? 22.16%. So if I have 1 plus 0.2216 times 0.2, so it's historically it's a 0.24432. So if you compare this to it is less than what we get from the budget system. What is the maximum? 0.2848.6. Okay, so now we can calculate also the historical payoff maximum, and we said it's your budget time plus minus your epsilon maximum, historical, of course. Now, if you have a budget, so now if you fix your budget here, you time it by this historical distortion, then we can say that H maximum, it should be, because X0 is 8,000, time plus minus 0.24432, which give you time 8,000. So which means the H maximum, it should be 1954.56 cost, and it is less than what we found by using the budget system. So we found 2,278. Now, historically, it's less. So which means something is not going well in your budget system, unless you have strong argument that this is the right ingredient, the right budget. That okay. So what can we do? Also, H max. So we can calculate the for the maximum duration. So the maximum duration, which is delta delta D, and we said it's a duration historical, and then I believe that we calculate the historical. It's 6 weeks, okay, and time by the epsilon max. So which means that delta the maximum buffer historically is 6 weeks time 6 weeks time 0.24432. Okay, divided by 8,000. Okay, 0.225 time 6. So approximately 2 weeks, more or less, but between 1 to 2 weeks. So this will be the maximum the duration that you can add on top of yours. So which means your total, this will be the buffer. So the maximum duration will be around 7 to 8 weeks historically. But but uh, uh, but for the system, it says 13 weeks. So you see how the using the equation of motion, and which is the governing equation, and the formulation that was developed in control system, how we can analyze the budget system accurately. I can add, so I can keep going here, so there is no end. Okay, so I will calculate the historical risk tolerance historical, and we said is 2 beta h, which equal c of the historical. This is historical time x0 time um, um, steady state. So now we can do something very, very interesting. So we know that the beta is given, h is the historical h is also computed here, which is this. So we can say that the historical h is 2 times systematic risk is 0.13 0.13094 time each 1954.56 equal C 0.310.31990 time delta x. Okay, so you can see the variation here. And then you can calculate the variation, and you have okay 2 times 0.13094 times 1954.56 divide by 0.31990. So we get delta x 1600, and you can evaluate the historical budget. Can you imagine that? Historical budget, which is which we can write x0 time distortion SS. And we fix this, we said it's 0.2. So which means the budget is 1600 divided by 0.2. So divide by 0.2, and it gives you exactly 8,000 something. So almost the same. So my budget here is almost 8,000.3151, almost 8,000, almost the same like the system, like the budget system. Now you ask yourself, how come is the same budget, but we get a different duration, different, what's going on here? It's a legit question. I will explain this. The issue is the distribution of the direct costs and indirect costs. So this is where the problem is coming. Okay, so now we know that the historical budget x0 is the same as the of the system, which is 8,000. Okay, now so we know the historical omega n square equal x0 historical divided by f0. So this will apply that f0 historical, of course, is 8,000.3151 over what's the new omega n? Omega n square. It's a 1.522. So it's a 1.522 squared. So if we divide this by 1.522 squared, we get, this is the new value, the historical value for the fixed cost. If you compare this to the historical, to the budget system, what you get, so we said 5,000, and the variable cost was 3,000. So the distribution is not, this is where the issue was coming from. So now what is your variable cost? Your variable cost or your direct cost, V0, is your X0 historical minus F0H, which will be, so time 1 negative plus 8,000.351. 3151. So it should be 4,546.6693 dollars. So this is the historical fixed cost and variable cost and the budget historically. So then it's up to the project management team or the estimator group to decide what is the best option for their to evaluate that particular activity. That's it for today, and we will elaborate more with the new concept in the next video. Hope that you like what I'm doing, and if so, hit the button like and don't forget to subscribe. Thank you very much.